Hello everyone, welcome back to my YouTube channel. I'm Chandana, pursuing 5th semester in the Department of Electronics and Communication Engineering at Sri Venkateswara College of Engineering, Bangalore. Subject Digital Signal Processing with the subject code BEC 502. And today I'm going to discuss about the topic classification of signals. These are the contents I'm going to discuss today. So before going to the classification of signals, let us know about signals. So signals are functions that convey information about the behavior or attributes of some phenomena. Importance: signals are fundamental in communication, control systems and data analysis. Classification of signals: continuous and discrete signals, even and odd signals, periodic and non-periodic signals, deterministic and random signals, energy and power signals, real and imaginary signals. Continuous and discrete signals: continuous time signals defined for every instant of time, representation that is x of t where t belongs to r, that is real numbers, and for example a sine wave sine 2 pi t and analog to audio signals. And discrete time signals defined only at specific intervals in time, and representation that is x of n where n belongs to integers, that is z. And sample version of sine wave is sine 2 pi n by n. So this is the graphical representation of continuous time signal and discrete time signals. Even and odd signals. So in the even signal we can see the continuous time and the discrete time. So now let us see about continuous time of even signals. So symmetric about vertical axis, that is x of t is equal to x of minus t. For example, cosine wave, that is x of t is equal to t square. And the discrete time, so symmetric about n is equal to 0, that is x of n is equal to x of minus n. So for example, x of n is equal to n square. And the odd signals also we can see the continuous time and the discrete time. So now let us see about the continuous time. So exhibits anti-symmetry, that is x of t is equal to minus x of minus t. For example, sine wave representation, that is sine t, and x of t is equal to t. And the discrete time, so exhibit anti-symmetry around n is equal to 0, that is x of n is equal to minus x minus n. For example, x of n is equal to n. So this is the graphical representation of even and odd signals. So this is also a graphical representation of even and odd signal, but we obtained from MATLAB tool. So when we write the code of even and odd signals, so we can get the graph like this. Periodic and non-periodic signals. So periodic signals in continuous time repeats after a period t, that is x of t plus t is equal to x of t. For example, cosine wave cos 2 pi t. So in discrete time repeats after n samples, that is x of n plus n is equal to x of n. For example, x of n is equal to sine 2 pi n by n. So in non-periodic signals, continuous time does not repeat over time, and for example exponential decay, that is e power minus t. So in discrete time does not repeat over samples, for example random sequence. So this is how the graphical representation of periodic and non-periodic signals look like. Deterministic and random signals. So in continuous time it can be described by mathematical equations, and for example x of t is equal to cos 2 pi t. So in discrete time predictable and can be exactly modeled. For example, x of n is equal to 3n plus 1. So in random signals, so that is in continuous time, so unpredictable and described using statistics. For example, noise in communication system. So discrete time characterized using probabilities, for example random bit sequence. So this is the graphical representation of deterministic signals and random signals. Energy and power signals. Energy signals in continuous time, finite energy and zero average power. So the mathematical representation of this is E is equal to integration of minus infinity to infinity mod of x of t square dt. For example, a decaying pulse. In discrete time, energy remains finite. The mathematical representation of this is E is equal to summation of minus infinity to infinity mod of x of n square. For example, a short pulse sequence. and power signals in continuous time, finite average power and infinite energy. The mathematical representation is P is equal to limit t tends to infinity 1 by 2t integration of minus t to t mod of x of t squared dt. For example, sinusoidal signals and in discrete time of power signals, power is finite and constant. P is equal to limit n tends to infinity 1 by 2n plus 1 summation of minus n to n mod of x of n square. For example, periodic sequence. So this is the graphical representation of energy signal and power signals. So in energy signals, the exponential signal is decreasing. So real and imaginary signals. Real signals in continuous time, all values are real numbers. For example, x of t is equal to cos t. And in discrete time, all samples are real. For example, x of n is equal to sine pi n by 4. In imaginary signals in continuous time, values are purely imaginary. So we can take the example of x of t is equal to j sine t. So j is imaginary, and discrete time samples are purely imaginary. Example, x of n is equal to j sine pi n by 4. So this is a graphical representation of real and imaginary signals. So this is the graphical representation of different signals. So this is a summarization of all the mathematical equation we discussed in the previous slides. Applications of signal classification, communication system, signal processing, biomedical applications, for example, ECG and EEG, and control systems. Thank you. Please do like, share, and subscribe to my YouTube channel, and stay tuned for more interesting videos like this. Thank you.